share my screen. So, hello again and welcome back to the course. We will talk today about group error correction codes, and our today's lectures will be organized as follows. First of all, we will get some mathematical background about what codes are considered to be group codes and how we need to calculate the amount of redundancy and redundancy symbols, and so on and so on. The next part will be group coding, encoding, the process of adding features to our code word to allow correction of errors. So that is called encoding. Then we will talk about, respectively, decoding, the opposite process when we check for errors and correct any errors we have found. We'll also, in mathematical background, talk about what is this group as a definition. And then we will talk about schematics for this encoding device and decoding device. We will create that as a logical schematic by using logical elements so that you can do the same for your task, your course project. If you have group code, you will be able to do that after these 3 lectures. If you have cyclic codes, you need just to wait 1 more week and you will be able to do the same. And this will be basically the first lecture today. This will be the second. And for the third lecture, we will have an example of course project calculations. So basically that would be working on our course project. I will show you for my example how to solve the task given to you in your course project. So that's what we will do today. And let us start with mathematical background. We won't get very deep, but we still need to define some terms, some things if we want to operate with the group code. First of all, we need to know what exactly is this term group in this context. So for error correction coding, basically we are working with linear algebra. That includes vectors, metrics, groups, and so on and so on. In this case, each of our binary code words can be represented as an integer number in decimal system. That's conversion from binary to decimal, yes. And this way, each code word can be considered to be just a number in our usual decimal system. And all the possible code words create the sets, very similar as to the set of natural numbers, the set of positive numbers, the set of integer numbers, and so on and so on. These similarly code words can create these sets. Yes, and these sets further are part of an algebraic structure. So the algebraic structure is not just the set of numbers, but it also includes some operations such as adding, subtracting, multiplying, division, and so on. So these algebraic operations are the only way explicit assignment of certain set element to a combination of 2 set elements, meaning that if we have 2 set elements, AI and AG, and we perform some kind of operations, which is denoted by this symbol, meaning that it can be any operation, yes, and we perform any operation between those 2 elements, then we will get another element, and all of these three elements must belong to the same set. This way, our algebraic operation doesn't leave the scope of our set. Yes, so we get, for example, we get in real numbers two numbers, 10 and 5. We add them together and we get number 15, which also belongs to the set of the real numbers. This works in a similar way to other structures as well. Just to mention that we can actually consider our set of real numbers to be different types of algebraic structure depending on what operations are we talking about. But in general, these operations can be very different. So there are direct, basic, or base operations, such as adding, multiplication, and maybe some others, but we'll talk about mostly these, which are, well, defined by themselves. The inverse algebraic operations are defined by using the direct operations. So meaning, for example, if we remember how in school we have been given knowledge about what is subtraction. Subtracting numbers means to find such a number AI so that adding it to AG, meaning that what we would resort to the addition operation to check this, would give us a key. So basically these operations, inverse operations, are defined by these base operations, and the base operations themselves are, well, defined separately, independently of the inverse operations. So this is an example of our often used operations: addition, multiplication, subtraction, and division. And two of them are direct operations, two of them are inverse operations. So what is exactly a group? A group is an algebraic structure. So this is a set of numbers with operation, and only one operation. It's either adding or multiplication, for example. Yes, so it cannot have both of the operations, meaning that the set of real numbers is actually not a group. It's something more difficult, more convoluted. Yes, because group just, for example, can be defined by using addition. You can get additional information about group and other types of the algebraic structure by following this link. And we will also return to this topic when we'll talk about cyclic codes next week. We will need to define such thing as ring and field algebraic structures. So we will talk about them next week. But for today, we are good to go with just this basic group definition, which also is as a basis for group codes. The group codes are named like this because actually they are based on the properties of these groups. So only one operation is defined, no inverse operations, yes, and multiple axioms are true for this case. So if all of these 3 points are true and the set of elements is complete, meaning that we cannot get any numbers outside of this set by adding them together. For example, consider the set of numbers from 0 to 9 and basic operation addition. If we add, for example, numbers 5 and 9, we would get number 14, which doesn't really belong to this set. Yes, so this cannot be group because we get as a result between two elements something that is outside of this group. So we need to do something differently. For example, we can use modulus addition like this. Mod 10, for example. In this way, we would calculate the remainder of this sum division with 10. So our 14 divided by 10 gives us the result of 1 and remainder 4. And this remainder is the answer of this operation, which belongs to this set. This is the example how we can use some more advanced operations. So this is addition by modulo 10. So what are these axioms that must be true in order for this set with single operation to be a group? First of all, the selected operation must be associative, meaning that the order of operation execution is irrelevant. We can either add, for example, A to B and then afterwards add C, or we can add first B and C and then A. That would give the same result. For addition and multiplication, it's usually true. However, mathematics is a complex science when you can actually have some specific operations when this might not be true. Yes, we just maybe in this course wouldn't deal with such operations, but of course mathematics can include such operations for which this just wouldn't be the same. For example, if we consider these numbers to be matrices, then for matrices this just cannot, it's possible that it wouldn't work, yes? So, next axiom is the identity element. It must be included into this set of the elements. So this set of elements must include some identity element which can be added or maybe performed an operation with it with any element which wouldn't change the value. So for addition operation, that is called a zero. So we add 0 to any number and the number is maintained. It didn't change. For multiplication operation, that is called one element. In this case, multiplication gives also the same result. But in general, this is called the identity element, which doesn't change the value of our element. Also, the third axiom, for each element, there must be an inverse element, so that operation between direct and inverse elements would give us identity value. So, for example, if we return to these operations, then addition and summation, then for addition we would need inverse element as minus a, which would give us the identity element of 0, and for multiplication we would need an element 1 divided by a, which is inverse by multiplication, which will give us our identity element 1. If all of these three requirements are true and the set of elements is complete, then that algebraic structure can be called a group. So, as you can imagine, the group codes form such a group. And for binary codes, of which we will talk, we are going to use the base operation exclusive OR. Also, mathematically the same thing as addition by modulo 2. So basically, this XOR operation is a logical function which gives the result of 1 only in the case if two numbers are different. So we are talking about binary codes, so our numbers can only be 1 or 0. And if these elements are different, the result is 1. If the elements are equal, 0 and 0 or 1 and 1, then the output of the XOR operation is 0. We will use this XOR operation as our base operation in these codes. Also, please note that in such a case, each element is automatically inverse to itself, since we add up together two zeros and get unity element, or two ones, we would either way get this unity element. So this automatically satisfies the third condition. Yes, we don't have to think about it any longer with this operation. Of course, we also satisfy the first condition with this operation since it's associative, and there are only two things we need to look for. First of all, we need identity element, which consists of only zeros of selected length. And we need to make sure that there is no way that after adding two numbers of this set, we get something that is outside of this set. So this way, it's quite simple to make this group. For example, let's see these three cases and check which of these are groups and which are not. So the first candidate doesn't include the unity element. It must include 0, 0, 0 in order to be a group. Well, the second condition doesn't hold here, so this is not a group. The second one also isn't a group, but because of different reason. Here we have that 0 elements, our unity element. However, if we, for example, select these two numbers and add them up together by using XOR operation, let me do that here. I'm going to write them one beneath each other and perform our basic operation with these two elements. Please note that also we are marking this modulo 2 addition by this circle around the plus sign. So it's not the same thing as just plus sign. This is a special operator. So let's calculate what is here. We are doing that bit by bit. So there is no carry in this case. So we just add up them and see what's happening. So 1 and 0 is 1. 0 and 1 is 1. 1 and 1 is 0. And 1 and 1 is 0. As we can see, there is no such element in this set. So we are outside of this set with this result, and therefore it cannot be group either. The last one, however, is a group. It is because it contains all possible numbers from 3 zeros to 3 ones. There is nothing else to be imagined here. It contains 0 element, and if we add up any of these two elements, we would irreversibly get something of these 8 numbers. Yes, so this is actually a group of these 3 examples. So this was just a demonstration which hopefully made you understand better what is group and what isn't. This is the set of numbers with an operation. Yes, this operation for our case is XOR operation or adding by modulo 2. Also, we can create a subgroup of our group. For example, consider that we select these 4 numbers as a subgroup. And for these 4 numbers, all the same axioms are also true, then it is a subgroup. If, for example, we select, for example, like this, it cannot be a subgroup since it doesn't contain zeros element, and it also can result in some element outside of the set. Yes, so a subset of these two numbers. We add them up together and we would get this number which didn't belong to here. Yes, so this cannot be a subgroup. This, however, case is a subgroup. You can check that, because if we add these two, we would get this one. If we add these two, we would get this one. If we add these two, we would get this one. So there is nothing obtained outside of this subgroup, yes. And it also includes the 0 element, so this is a legit subgroup. So for the group code, it turns out that we have, let me remind you of what we talked last week. Last week we talked about how these codes can operate and find and correct errors. The idea was very simple. We created allowed code words and restricted code words. So only allowed code words can be output by the encoding device. If we receive restricted code word, then it means that there is an error. The idea is quite simple and straightforward, right? And we also calculated that these allowed code words are only a fraction of all possible code words. So basically, we have M0 allowed code words, which is 2 power k, yes, and all the possible code words would be m, which is 2 power m, small, yes. And m is the length of the code word, while k is the code, yes, while k is actually the length of data which we would like to transmit. So the difference and length of data. So the difference is actually some control or check symbols, yes, which is m minus k. And we need any of these symbols we'd like to add. But first of all, let's point out that for the group code, all possible code words, these form a group. So this set of all possible code words is a group by all the definitions, while allowed code words, which are only a part of this set, subgroup. Sorry, someone is there. And okay. So the allowed code words form a subgroup as a part of a larger group which consists of all possible code words. That's why these codes are called group codes. And we are talking about some specific Hamming group codes. Sorry, it's A, not E, Hamming group codes proposed by mathematician Hamming. These codes will be able to correct one error per m symbols. Basic operation is XOR operation, and code word length in this case is m. So we need to know how many of these m symbols. For example, I'm having m equal to 7, and I need to know how many of these 7 symbols will contain data and how many symbols will contain check symbols, correction symbols, yes? Let's talk about this, and then we will be able to actually calculate these correction symbols. So it's okay here, and so the procedure is quite simple. First of all, we define how many check symbols we need. This largely depends on the number of errors to be corrected. So if we would like to correct only one error, we would need, for example, one value of error. If we'd like to correct 2 errors, we will need greater value of error, and so on. Then, if we know how many symbols we need, then we can calculate these check symbols based on data to be transmitted. So we have some data to be transmitted, and we use this data as input for our check symbols calculations. So basically we have data from which we calculate control or check, and then at the step 3 we merge them together. So we have data matched with control. This forms the code word, and the amount of data is K, the amount of control symbols is R, and in total we have the sum K plus R. And this code word is what we transmit, receive, and find errors in, and correct if we are capable of that. So, how many control symbols or check symbols do we need? Well, it actually depends on the number of errors to be corrected. Let's consider, for example, the case of 7 symbols to be transmitted, which include both data and control. And we need to tell how many of the symbols are control symbols. Then, of course, it will be quite easy to tell how many of the symbols will be data symbols. So let's assume that we are talking about single error correction code, which is capable of correcting only one error. And then one error can happen in 7 possible ways. The error can be in the first symbol, in the second, third, and so on, up to 7th. In total, m possible ways of this error. And in order to be able to correct this error after we received this code word with error, we need unique syndrome for each of the errors. So for example, for this error, we have such syndrome. For this error, we would have different syndrome, and no similar syndromes are here. Each of these error vectors, error combinations, yes, has its own syndrome. If, however, for example, assume that we happen to have same syndrome for 2 different errors. In this case, it would be impossible to tell where the error has happened, because during the decoding procedure, we calculate the syndrome. So we have calculated the syndrome, and the syndrome says us 1, 1, 1. And then we cannot define where exactly that error was, because these 2 error types have the same syndrome. So in order to avoid such things, we are making sure that each of the errors has a different syndrome. This way, we will be able to tell with 100% guarantee that the error was exactly there. Well, as you will see at the end of this day, it turns out that not 100% after all, but well, considering that we selected the code correctly, because we also need to make a choice of the code, we cannot just assume that this code will work for us good. We need to make some research on the channel and select the codes which would be suitable for such a channel. We will talk about that later, especially when we will finalize our course project. But for now, we are assuming that that is what we did, and our selection is good. So this is quite simple. And make note, please, that there is no syndrome 000 in this table. Yes, here are only non-zero syndromes. The 000 syndrome is reserved for the case when there are no errors, because, well, we need some way to tell that everything is okay. So the syndrome is 0, then no errors. If the syndrome is not 0, we find what exactly is that syndrome, and then we locate the error, and then we can correct that error. So that's how it works, yes? So how I was able to find out that I need 3 numbers for each syndrome? Well, basically because the 7 different numbers in binary system requires 3 bits. Yes, we cannot make it with 2 bits, because 2 bits would only be able to allow us numbering in this range and no further. And we would have to repeat those syndromes, and that would, well, be bad, yes. So, So that way we wouldn't be able to correct the errors. We also cannot, well, we can, but we don't need to use 4 bits, because with 4 bits we can cover much larger range. We can actually cover up to 16 symbols. Well, excluding the all zero syndrome, it's actually 15, right? And we only have 7. So 7 requires exactly 3 bits. We'll talk about that right now, but first let's try and make that as a formula, how we can calculate. So if we are talking about only a single error correction, then we have m possible error types or combinations or cases, scenarios. We can call it any way we like, yes. So as in this table, for example, each possible scenario was represented by its own row, a total of m rows. And also there is one more syndrome needed for correct receiving, yes, that the case without errors. So in total we need m+1 syndromes, and for these syndromes we need log 2 of that number bits per each syndrome, right? So basically this way we also find that number 3, because log 2 of the 7 plus 1 is exactly 3. And that's why I used 3 bits per each syndrome. That +1 came from the syndrome for the case without errors. Yes, then no errors have happened. Then, actually, it turns out that not always we will have m such convenient value that it would give us precise value. For example, let's consider m equal 10. In this case, log 2 of the 11 would actually be something between 3 and 4. It would be a fractional number which we need to round. And we always select the higher value because of the same reason. Yes, we can have, for example, in this case, 10 possible errors. So the error in the first, second, third, fourth, and so on, and 10th symbol. If we use syndrome from 3 bits, then we would inevitably be forced to start repeating these syndromes. So on, and somewhere here, those syndromes would start to repeat themselves. This way, we would not be able to determine where exactly the error has happened, because not all syndromes are unique. So we need to use 4 bits per each syndrome, although it can provide numbering by up to 15 and we need only 10. Well, in this case, our code is not optimal because we could have added more information to the same number of correction bits, but we didn't. Yes, well, it's basically some type of the so-called shortened code. Shortened, which also can be used. And then consider the case when we need to correct 2 errors per code word. For example, the same number of errors, 7. No, not errors, but code word length 7. And we'd like to be able to correct any combination of 2 errors in these 7 symbols. So we send some 7 symbols from A1 to A7. And somewhere here 2 errors have happened. And we want to be able to correct any combination of these 2 errors. Of course, this also includes the correction of 1 error too, because the codes that can correct 2 errors must be able to correct 1 error as well. So we need to add up the total number of syndromes like this. First of all, we need the syndrome for the case when no errors have happened. Usually, we use all zero syndrome for this case. Then, we need all the syndromes for a single error, which already has been discussed, is total number of m, which also can be calculated as a number of combination by 1 from m symbols, which just happens to be exactly m. That would be the syndromes for single error. Now for double error syndromes, we need to calculate combination by 2 from m, and then we add them up all together and calculate the logarithm by the base 2 of that value, and would get this r. So, for example, in this case, if our m is 7, then number of combinations by 1 from 7 would be 7. Number of combinations by 2 from 7 would be 21. 21 possible way of how we can make 2 errors in 7 bits, plus single errors, plus plus 7, plus 1 for no errors case. That would give total of 29, and logarithm of 29 would be 4 point something, which we round to the closest larger integer number, 5. Meaning that of these 7 symbols, only 2 symbols would send data, and 5 would be calculated to correct for the errors, which is a lot of redundancy. Yes, consider that we actually are sending like 3.5 times more data than we need to be able to correct 2 errors, which is a lot, yes, but this is also the question of reliability. If we need that data received correctly, then we might just have to do it. Also, M7 is quite short code, but this will keep for longer codes as well, when we will need to actually spend more data bits for correction symbols than for data to be transmitted. So this way we calculate the number of these correction bits. Now, how do we calculate these bits and where do we place them? Let's start talking about group coding. Yes, okay, it's here. About group coding, about Hamming group coding in particular, which corrects a single error. So we need the list of possible syndromes and the list of possible error vectors. For Hamming group code, this approach is very simple and straightforward. The syndrome value shows where the error has occurred. For example, if we have received the code word of 7 bits and we found our error is here in the third symbol, then the syndrome would be equal to 3 in binary form. So this is 3 in binary form, yes. And this way it works for Hamming group codes. For example, for error in symbol 7, the syndrome would have been 3 ones, 7. For syndrome in first symbol, it would be 1, and so on. The idea is quite simple, straightforward, and it also makes an efficient coding. So we can create a table of these error vectors and matching syndromes. So for the error in the first symbol, we have 1 in binary form. For the error in second, 2, 3, and up to 7. Yes. So this is the 7th symbol. This is the first symbol. And we'll use this table to make coding equations which calculate the correction or control bits. Currently, we are not differentiating them, which of them are data bits or which of them are control symbols. It's irrelevant yet. We will define them after few minutes. Where are control symbols and where are data symbols. So if you're having m equal, for example, 21, then you would need error vector consisting of 21 bit in length, and there will be total of 21 of these bits, of these rows, yes. And syndromes will be also in binary form from 1 to m to 21. Yes, so basically this table is quite simple and straightforward to prepare, and we will use it to create equations for coding and decoding procedure. So, how do we perform encoding and calculate the control bits? The idea is very simple. We are using these syndrome rows. Let me show you it like this. For example, we are going to use this first column for the first equation, the second column for the second equation, and the third column for the third equation. So each of these columns define a coding equation, and we will have a total of 3 of such equations. Now, let's return to the case of m equal to 21. In that case, we would have r equal to 5, and we would need 5 columns, 5 equations. So, let's make our first equation. How is it formed? Basically, what we are doing is multiply the symbol notation, yes, with a syndrome value in this column. So for this column we have 0, here we have 0, here we have 0, and they are marked with red, and here we have ones. So it would be either this symbol will stay or it go away, because multiplication by 0 gives 0, and this eliminates this symbol from the equation. Yes, we basically multiply this column with this column. These are symbols for us like unknown, yes, and we set this sum equal to 0. So this way we are making an equation. So basically only the symbols which have ones in the syndrome column are staying in the equation. So for this case, A1, A2, and A3 didn't make it to this equation because they have zeros here. And we are leaving only A4, A5, A6, A7 in this equation because they have 1 elements. And we calculate this sum and set it equal to 0. That is our first equation for syndrome S1. Similarly, we are doing that for 2 remaining columns. So, for the second equation, we have A2, A3, A6, and A7 with 1 in the column of the syndrome. Yes, you can see here is 1, 1, here, and here. Other symbols have zeros. So we add up together only those which have ones in the corresponding column. That would be A2, A3, A6, and A7 in this particular case. And the third equation in the same way. So we have A1 with 1, A3, A5, and A7. And we add them up together and set equal to 0. So this gives us the set of the system of the 3 equations. And in these equations, we don't really know yet which of the symbols are correction symbols or control symbols and which of them are data symbols. We only know that for our m equal to 7, we need 3 correction symbols and 4 data symbols. Well, because that was actually the first step, what we did, we calculated R as log 2 from m plus 1. And this way we find out that R is 3, and that's why we used 3 bits per syndrome in this table part. So basically here we have R columns. So let us select from each of the equations one symbol which is unique to this system. What I mean is that, for example, in the first equation, we select symbol A4, which doesn't show up in any other equation. So, for example, we cannot choose A6 because A6 is also present here. Yes, that is not a good option. We cannot select A7 either. It's present in 3 equations. And the only possible ways would be to select A4, which isn't present in any other equations, A2 and A1. They have been in these equations in the first positions, but it doesn't necessarily has to be this way. Yes, you just need to select the unique per each equation, so it doesn't show up in any other equations. Well, basically this has happened because these symbols in binary form contain only one element of 1, yes? So that would be A1, A2, and A4. And they are, in fact, positioned in the power of 2 locations. So that would be power of 2 by 0, 1 squared. The next one would be A8. Here we would have control symbol. That would be 3. Then 16, 32, and so on. That's how it works, yes? So currently we are talking about non-systematic coding because it has a nice property of which shows up during correction of errors. So for non-systematic encoding, it has been obtained like this automatically from if we follow this procedure. Yes, we get these equations, we select these symbols to be control. The remaining is actually a data. So these control symbols are in positions 1, 2, and 4, which is not in the order, yes. You can see that, for example, we have control symbol, information symbol, control symbol. So the symbols are mixed together, yes. They are not presented like, for example, information symbols like this and control symbols like this separately, yes. So this would have been systematic coding. But what we have obtained here is actually non-systematic. Yes, these just have happened like this for our coding. We will talk later about what we need to change to make that code systematic. And of course, we will lose something in the process, and what exactly that will be, it will be clear after we understand how it works. So for now, we are talking about non-systematic coding, and we also make new notations, adding E symbols as check or control symbols and C symbols as data symbols. In this way, this very same set of the equations can be rewritten in this form. So these control symbols are calculated as sums of modulo 2, this is addition by modulo 2, from the information symbols. So the algorithm is pretty simple, right? We need to select some numbers, add them up together, and we would get these control symbols. So, okay, and let's see example. And then we will make a little break. So, consider the following data. We already know that we need k equal to 4 data symbols because we have calculated that our r is 3 and k is actually m minus r. So that would be 4. And we have selected this data to be transmitted. So actually this is what our system transmits from receiver or from transmitter to the receiver, some data, which we are trying to protect from errors. So C1 is 1 here, and C2 is 0, C3 is 1, and C4 is 0. Our task is to calculate the control or check symbols E1, E2, and E3. Right? So, we are just going to use this set of equations and put inside, substitute these numbers in the corresponding position. So C2 is 0, it's here, C3 is 1, and C4 is 0. So these equations can be quite long, especially if you have m equal to 20 or 30. Yes, then you will have a lot of numbers here. But it's sufficient to know that actually it's quite simple to calculate this sum by modulo 2 from many numbers. So, for example, let me write you this much more numbers to be added up together by this operation. I'm trying to think them randomly, but of course this human randomness is not so random as you can imagine, but still it's not relevant. I'm just trying to show you how can we calculate this fast, not without the need to actually sum everything together and so on and so on. Well, a few more. What I would need to do is actually to calculate 1 plus 0, that would be 1, plus 1, that would be 0, and so on, so on. But there is a much simpler and easier way. What I'm going to do is to count how many 1 symbols I'm having here. That's 1, 2, 3, 4, 5, 6, 7. 7 symbols. 7 mod 2 is 1. So the answer is 1. Yes, if we have odd number of 1 symbols, then we have 1. If we have even number of 1 symbols, then they all compensate each other by giving zeros. Yes, and if there is odd even number of these ones, then we can make finite number of these pairs. Each pair would give us 0, and zeros summed with zeros would still give us 0. If we have, however, odd number of ones, then we will have 1 symbol without a pair, which would lead to this 1 value. So, following this logic, we have here only 1 symbol 1, that would be 1. Here we have 2, which is even, 0. Here we have 1, which is odd, 1. So the control bits, the control symbols, the check bits, for this particular data block will be 1, 0, 1. Of course, for different data block, these symbols would be different. So, for example, 1, 0, 1, 1. We have changed C4. Now it's 1, 1, and 1. And this way we would get 0, 1, 0 control bits, right? So we calculate the control bits from information bits and then send them together by putting them in non-systematic code word. Here we have control bit A1. Here we have control bit A2, C1, A3, C2, C3, and C4. That is our code word to be transmitted. Now, we can also make that in matrix form, and this is actually very efficient for computers, and we will use that for our simulation later. So let me explain you how this matrix is formed. Basically, it's quite simple. So we try to represent these equations in form of the matrix, where each row is each equation. So here we don't have C1, yes, so in position of C1 we have 0, we have C2, C3, and C4. So here we have 1s, 1, and 1. Now, for the second equation, we don't have C2, right? You cannot see it here, and all the others are present. And for the last equation, we don't have C3, while others are present. So this matrix is written up like this in quite simple way, and we can use that to make coding process in matrix form. Moreover, we can actually in one go create the entire code word, not just calculate the control bits, but make the entire code word. So please note that we had transpose operation here, so basically that would be the first column. And that was in fact E3. Yes, so we have here E3 and here we have E1. Please don't be confused, don't miss that, because, well, actually this way our syndromes would be opposite if we are making mistake here. So make sure you didn't lose that information, that the first row was actually E3, not E1. So here we have E3 as a column here, E2 as a column here, and E1 as a column here. What we need to fill in the remaining positions? Well, actually there is nothing different than identity matrix, well, only separated with this E3 symbol. Yes, so basically we don't want to change our data C symbols, we want them to be like they were originally, and we want to add together before and in between these control symbols. So this way we have developed the coding matrix, encoding matrix, which can be used, for example, in Octave or MATLAB. I will show you on our third lecture how to do that, and you will need to make that encoding matrix anyway for your sixth task. Yes, so I will show you how to do that and how to use it to make encoding process in one go. And the only thing that we need to be aware of, that matrix multiplication involves the regular addition, meaning that we will have 1 plus 1 equal to 2, not 0. So in order to alleviate that, we need, after we have calculated matrix multiplication, to take modulus 2, meaning we need to divide by 2 and find the remainder of that division. Well, actually, in MATLAB or Octave, we have such operations such as mod or remainder. Even in C programming language, we have this remainder calculation operator as this percentage sign. So if we multiply our data block with this matrix, as a result, we would get already formatted and complete code word, which is very convenient and nice. And also, we can actually this way calculate many code words at the same go. For example, I'm going to add few more code words and so on, as much as our computer memory can hold. Yes, and this way we would calculate this matrix multiplication, for example, for 1000 code words in just a single go. which is very efficient. And that's what we will going to use for simulation. Now, before we are talking about decoding, let us make a short break for 17 minutes and continue at 13:50. Yes, then we will talk about decoding and schematics. So see you in 17 minutes. Thank you for attention for now, and we'll continue later.